Hey everyone, today I'm going to give you a little bit more information on when to use the power rule. This is going to be a build off of my last video that I covered, the very basics of the power rule. But I'm going to start with when to not use the power rule, and this is really when you're going to be dealing with some trigonometric functions like cosine, sine, your tangent functions, um, anything with a fraction like this. There's an easier method that we can use for this. Um, the derivative of, say, 5 to the x is another example of this. This is ln of 5 equals 5 to the x. I'll cover that in a separate video at a later time. And e to the 2x. You can see that none of these are really easily applicable with the power rule. Those are all other examples with different methods that can be covered later. Some examples that we're going to cover today are a bunch of different derivatives that use the plus in there. We're going to do some fractions that are going to give us some negative exponents. Here you see we have another exponent, and then this is, there could be two methods for this last one, and I'm going to touch on that once we get down to that example. So let's start with the power rule by definition. So we know the power rule by definition is the derivative of x to the n equals n times x to the n minus 1. So for this first example, we can see that there are two terms that we were taking the derivative of here. So the nice thing about derivatives is you can actually separate them with this plus in the middle. So this is really equal to d over dx of x to the fifth plus d over dx times 3x. So now we can take the derivative of each term separately, like they're each own individual functions. So let's do this real quick. So we know for the first one, n is equal to 5. And by the rule, we know that the derivative of x to the fifth is 5x to the 5 minus 1. Okay? So we see we have our n term here, and we subtracted 1 in the exponent. Now we can see that n in the second one is equal to 1 because there's really an imaginary 1 above the x there. So we can do plus 3 times n, which is 1, and 3 is our leading coefficient here, so we have to bring it in front. And we do x times 1 minus 1. Now, we know that 1 minus 1 is 0, and we know that x to the 0 really equals 1. So let's simplify this a little bit. So this is really equal to 5x to the fourth plus 3 times 1, because x to the 0 equals 1, which is equal to 5x to the fourth plus 3. So, and we have our derivative for the first example there. Now, let's touch on the second one. So the second derivative is a very similar concept to the first, except now we have this radical we're dealing with here. So let's rewrite this radical a little bit. Let's do something quick on the side. So we know that radical 3x is really equal to radical 3 times radical x, which is equal to radical 3 times x to the 1 half. So let's rewrite this in our equation. So we can do d over dx of radical 3 x to the 1 half plus 3x squared. Now let's rewrite this like we did in our first one, separate those terms. So d over dx, radical 3x squared, or I'm sorry, to the 1 half, plus d over dx of 3x squared. And once again, these x in the denominator, that's just what we're taking the derivative of. And in calculus 1, we're really only using one variable. In calculus 2, you also have some y terms mixed in there. And I'm sorry, calculus 2 and calculus 3, you have some y terms mixed in there in a multivariable calculus. But let's stick to this for now. A lot of times with a leading coefficient, you can actually just bring them out front here and completely ignore that. So let's take the derivative of this first term. So we know that here n equals 1 over 2. All right, so this equals 1 over 2 times radical 3 x to the 1 half minus 1. All right, so there's the first term straight down here plus we put those in brackets, plus the derivative of 3x squared. And we know that is another simpler one, n equals 2. Put some more parentheses there. So n equals 2. So we do 3 times 2, because 3 is our leading coefficient, and 2 is our n term, times x squared minus 1. And then once again, we're just subtracting 1 in that numerator there. All right, and rewrite. We get, oh boy, 1 over 2. Actually, let's do radical 3 over 2, x to the negative 1/2 plus 6x, and there's an imaginary, put this in right, there's a little 1 there. But that won't be in our final answer. So we can see here that we have a negative exponent, and we really don't want that. That's not good practice to keep. So we can get rid of that by sending that down to the denominator here, and it'll be positive. So radical 3 over 2, x to the 1/2 plus 6x. Okay, make sure everything looks good. And we know that x to the 1/2 is really equal to radical x plus 6x. And there you have your second derivative. See, it's very similar to the first. The big thing is just really separating that plus and distributing the derivative terms. Let's take a look at this one. So this one looks a little bit more complicated because we have the x in the denominator, but it's really a lot easier than you might think. So we really know that this is equal to d over dx of x to the negative second, right? Because 1 over x squared equals x to the negative second if you rewrite it. And once again, we can just see here that n equals 2. So let's, I'm sorry, this is negative 2 here. That's important. So when you multiply by n, you bring negative 2 to the front, x to the negative 2 minus 1 in the exponent. Once again, always subtracting by negative 1 here, n minus 1, and this is n minus 1 here. All right, pull this forward, negative 2, x to the negative 3. And once again, let's send that to the denominator to make it positive, and that's negative 2 over x to the third. It's not really as difficult as it first looks. It's really just bringing your x term to the numerator to be able to pull your n out. And even though it's negative, we can still multiply by your n term in front, and it will show up in our final answer like so. Next one, example 4. This one is a little bit more complicated because we're dealing with a little bit more algebra here, but we can do a quick aside term, and we can figure out what x to the 5th over radical x cubed is. All right, so let's start by rewriting x, or square root of x cubed, and this is going to be x to the 3 over 2. All right, and then when you're dividing the terms, you subtract them. So we're going to do x to the 5 minus 3 over 2, and this is going to equal 7 halves. All right, and once again, just like we did before, n equals 7 halves. Bring this down to the front. So we're going to do multiply by our n term here. So this is going to be 7 halves x to the 7 halves minus 1, which is equal to 7 halves x to the 5 halves. And there is your derivative for example 4. Let me circle that for you. And once again, it's just doing some simple algebra to make sure you get that equivalent value up here. Example 5. Once again, we're just doing some more negative exponents here, and this is just a single leading value. So we're actually going to see that this will drop to 0 because there's no x term when you're taking the derivative here. So let's rewrite this. D over dx 5 plus d over dx of 3x to the negative 1. So when you take the derivative of this, since there is no x term here with the 5, this will actually go to 0. All right, so we're going to get 0 plus, over here, you see n is equal to negative 1. Once again, we're going to bring n down to the front. So we're going to get 3 times negative 1, x to the negative 1 minus 1. And up here, once again, we just have our n, we have our n minus 1 term. Multiply this out, and you get negative 3x to the negative 2. Drop this down to make it positive. So we're going to get negative 3 over x squared as our derivative. So the biggest thing here is when you take the derivative of an integer that doesn't have your derivative term in it. So in this case, there's no x here. This is just going to go to 0. If there was an x here, however, this would be equal to 5 because the derivative of 5x is 5. But we're going to get rid of that for now because there's no x there. So that's your derivative for example 5. Example 6. We're going to start by distributing this 5x out into this term. So 5x times, rewrite this actually. So 5x times 3x is going to give us 15x squared plus 10x. Okay? And then distribute this out into our second terms. D over dx of 15x squared plus d over dx of 10x. All right, now let's take our derivatives. So n equals 2 here, and n equals 1 because there's an imaginary 1 there. So this is going to equal 15 times 2, x to the 2 minus 1, plus 10 times 1 times x to the 1 minus 1. And we know 1 minus 1 is 0. And when you do x to the 0, that just equals 1. Let's rewrite this a little bit more. So we have 30x, there's an imaginary 1, plus 10, and that's your derivative using the power rule. And once again, I'll just scroll to the top here, and you can take a look, try these examples for yourself, and see if you get a similar answer. You can also go to derivative calculator.com, and that will help you with a lot of your derivatives and practicing as well. Thanks for watching.